So what are X-rays? So X-rays are part of electromagnetic spectrum with some energies or frequency range or wavelength range, you can say. So definitely, if you draw the electromagnetic spectrum with energy increasing in the order like this, at the bottommost, what you find is called the radio waves, which are the lowest energy waves. And once you proceed from the radio wave, what you call is called microwave. Then from microwave, you go further to reach the infrared, and then you reach the visible spectrum. Then UV light comes after that, and now comes the X-ray. And then we have gamma rays. And the top of the ladder is called the cosmic rays. Okay. So definitely the X-ray comes in a very high energy range, and we know that energy of a wave depends on the electronic transition. So if we have two orbits, let's say the n equals to some value, this is m, and if you go from here to here, so if the electron will jump from the high orbit to the low energy orbit, it will release some energy packets or the photons, and the energy of this photon will be equals to the difference of energy level. So to get the high energy radiation, sorry, that's gamma, my bad, gamma. I'm talking about the X here. So depending on the energy difference, we can achieve the uh, energy value which we call X-ray. So X-rays are having certain range in for which we have given a name it X ray. Okay. So generally a wavelength belonging to the range from 0.1 angstrom to 100 angstrom. This range of wavelength we call it X-ray. So they are defined by the energy value or the wavelength value. So this is the X-ray. Okay. So now the question is how to obtain this level of energy. So if you try to find the E max, the maximum energy that we can create, then this will be SC by lambda, and SC is 12,400 electron volt angstrom. Upon lambda we have 0.1 angstrom. So this turns out to be okay. You can see this is like a 124 kilo electron volt. So this is the kind of energy level we can think of, and similarly, you can go for the minimum value will be 12,400 EV angstrom upon 100 angstrom, which will give you 124 EV, which is like 0.124 KE. Okay.
Yes.
Okay. So the energy range you can see this is from 0.1 to 4. I mean, this is just a rough, I mean, approximation. It's not something exact. But this gives you the idea that the X-rays are in the range of kilo electron volt. So this is what you need to remember, that X-rays, the energy of X-rays in the keV, kilo electron volt. And if you remember the H-like atom, so for H-like atom, the energy which you can get is 13.6 into Z square maximum. Okay, electron volt. And Z will go from 1 to 4, 1 to 3, hydrogen, helium, lithium, and beryllium. 1 to 4. So maximum you can get is 13.6 into 16 electron volt, and definitely this value is very small compared to the actual value of X-ray. So that is why we say that uh, H atom or H like atom won't be able to create energy range equivalent of X-rays. Okay. So even if you remember the various spectrum in the H atom, we have the Lyman, Balmer, Paschen, Pfund, Humphrey bracket also. So Lyman, Balmer, then Paschen, bracket, and then Humphrey. Whatever, Humphrey, Humphrey. Now these are the various series or spectrum, and they talk about from UV to infra only. So there is no X-ray possible in the H-like atom. So that's why the property of X-ray emission is only thought about in case of high atomic number elements. So we have generally heavier elements, the D block elements like cobalt, zinc, nickel, or maybe chromium. So these are the heavy metals in which such energy transition can produce such a high energy X-rays. So first of all, the X-ray is not going to be emitted by any random element. We need an element with certain atomic number and beyond, because only in that case things are possible. So what exactly we do in the X-ray? So the method of production of X-ray, I mean, we have the arrangement called the Coolidge tube experiment. So in this Coolidge tube experiment, we have something like so now we have a metal target. we have something like a groove, and within this groove we have a metal specimen. So we call it metal specimen, which we just put inside. And let me move this. So this is the arrangement of. So this is the target. This is called target metal. So you can keep on changing. So this is the fixed groove. The white part is a fixed groove, and the red part is the metal which you want to experiment with. So we call it target metal. And on the left side we have something called electrode, and this electrode is fitted with some sort of filament to produce the heat. And because of the heating process, these electrode will get heated and will start emitting electrons. So now generally this electrode is attached to a negative potential, and this is connected to a positive potential. And because we want the potential or the energy to be in the kilo electron volt, so this potential is also in the kilo electron volt. So maybe roughly we can take up to 10,000. Okay. So now the voltage you have to keep in thousands or 10,000s of volts. So generally we keep at let's say 10,000 volts, because what we want is a large energy value. Now what we encounter here as a result of the process of heating process, we have thermal or thermally excited electrons. These are called thermally excited electrons, or called thermions. And the thermionic emission, this process called thermionic emission. So earlier the television set used to have the CRT, and the CRT is called cathode ray tube, and cathode ray tube works on the principle of thermionic emission only. And thermionic emission follows the Richardson Dashman or Dushman, whatever equation. It's called the RD equation. So American and German collaboration, you can say. Richardson is American, Dashman is German, basically. I never thought of asking when finding his full name. But this equation governs the thermionic emission, and it is given by the formula. The thermionic current, we call it thermionic current, is equals to A S T square. So A is called RD constant, that is Richardson Dashman constant. S is called surface area. E is called absolute temperature. Y is called work function of the cathode, and AB is called Boltzmann. Now again, the Boltzmann is also let's say, German only, Ludwig Boltzmann, and he's the father of statistical physics. Okay, so the thermonic current is AST per e power minus 5 by kT, and if you take the log both sides, so let's say if I take the log of I, so I can take log of AST square at one side, uh, and the other is log of e power minus 5 by kBt, which will become minus 5 by kBt, and log of current is equals to, because A is t squares, we can write log as plus 2 log t minus 5 by kBt. So we have the relationship between the log I versus temperature relationship. Okay, and if I differentiate this, what will happen? D by dt of log I equals to 2 by t minus plus not use. So they may ask you some sort of maybe a diagram between one variable or the other variable. So depending on what they ask, we have to convert this into. So generally, these kind of graphs are asked on the logarithmic scale. Now, once the thermions are emitted, once we have these electrons coming out of the electrode because of the heating process, the negative potential will repel them. Negatively charged, and this is positively charged. So these electrons will be repelled, and so even though they will have some kinetic energy in the very beginning, but they will accelerate towards the target metal. So when these electrons having almost energy, so I'm okay. We know that they will have some energy in the very beginning, but the voltage is so high that the final kinetic energy reaching the target metal will be very high, and we know that the kinetic energy at a node will be how much? So kinetic energy initial plus EV. Understood? So if the kinetic energy here is KEI, then kinetic energy at a node, which this is the node, will be KEI plus EV, and generally we ignore the KEI because since in practical case KEI is very small compared to EV, so the kinetic energy at a node we keep as EV itself, and the moment they will come near the target, these electrons will hit the target metal, and in the process of heating the target metal, they will lose a part of fraction of their kinetic energy. So this is not the one electron which is hitting. We have like millions and trillions of electrons coming and hitting the target metal at once, and therefore every electron will lose a fraction of their energy, and the fraction will be from more than zero to less than one. Because the chance that they will lose 100% of the energy due to the impact is negligible, because it's like a probabilistic idea. So the electron coming from the electrode and hitting the target metal cannot create or cannot lose 100% energy. And after hitting the target, the energy which they lost, the kinetic energy which the electron will lose, that will convert into X-ray radiation. So this X-ray will come, and we will have a kind of window here, and this is the X-ray. So as a result of infinite impact, I can say. So electrons are hitting the target metal, and thereby they are losing the fraction of their energy. Now, because the fraction can have any value, so we can get a energy value anywhere between we can say energy lost due to impact with target metal will be from 0 to EV value. So now you cannot lose this much. So it will be more than 0, less than EV. And every electron, in fact, will undergo multiple collision, not just one collision. So it will hit the first layer, maybe it will go into the next layer of the target metal, will hit the another layer, then again next, then another layer. So it will have some randomness in terms of the layer which they penetrate, and the X-ray will have different values of energy. And if you plot such energy, because infinite number of photon and electrons are hitting the target, so X-ray which will be coming here, so if you plot the intensity of X-ray, like intensity means how many such wavelengths are coming per unit time, per unit area. So if you plot the intensity of X-ray with lambda intensity, you can also think as a probability. So the minimum wavelength that we can emit is how much? So theoretically, there is something called threshold wavelength, which is minimum wavelength that is theoretically possible. Okay. So the threshold value, also called the minimum value. So we call it lambda minimum, or we can say lambda TH, or threshold. So we know that energy we write as SC by lambda. So when lambda will be minimum, then energy is maximum. So this we can equate with EV, because that is the maximum energy. So the E max is lambda minimum. So lambda minimum turns out to be Hc by Ev. So we cannot emit a wavelength less than this value. So this is the beginning will be at some lambda minimum. So we cannot have the X-ray in this region. Not possible. Okay. And now if you plot the graph will look fairly smooth. And then suddenly you will see a spike. So so graph will be continuous with some random spike, and you will see some more spikes. We only consider the first two spikes and then we continue the graph as usual. So the blue color graph is called continuous X-ray, and the spike we call characteristic X-ray. So these are spikes. The spikes represents X-ray. So continuous X-ray is due to the loss of kinetic energy of electron. Let me define this. Now the cause of the characteristic X-ray is different. So characteristic X-ray is quite different, and it is due to transition of electron within the atom of target metal. So it is due to the transition of electron within the atom of target matter. So the reason behind the characteristic X-ray is quite different from the reason behind the continuous X-ray, and even the continuous X-ray can be divided into two categories. So continuous X-ray, we can call it hard and soft. So hard means high energy, and soft means low energy. So when we talk about the X-ray filmography, so let's say when you go for the X-ray in various diagnostic center, so they are supposed to use the soft X-ray, and they expose the X-ray to your body for a fraction of second, so that it should not damage the other tissues. So rigorous, or you can say multiple X-ray, will lead to some sort of cell mutation, which is also danger, or maybe it can cause cancer also. So one should not go very often to the X-ray center for one reason or another. Anyway, so continuous X-ray can be hard and soft depending on the high energy and low energy. Okay. So now our interest is basically on the characteristic X-ray, and we'll try to understand the graph also. So graph which we have drawn here. This spike represents lambda k beta. This represents lambda k alpha. This is lambda L beta. This is lambda L alpha. We can also have the k l m n o p like this, but we stop at the first two because these two are slightly significant, and later on things are not significant. So the spikes are very small like this, and you can ignore it. So now the actual question was how the characteristics suddenly came into picture. So we have a atom. So we have an atom. This is the nucleus, and the orbits are like this. And they have the orbiting electrons as usual. And so on. So when we have the X-ray or the thermonic emission, the electrons are coming towards the metal. So sometime in the due process of collision, they can knock out the electron itself from the target element. So sometime what happens? So one electron will come and they will knock out the electrons, and by doing so, they create a vacuum, or you can say empty orbit. So the moment you create a gap, so we have one electron, now we have electrons here, and we have here again, main, and we have more also. So the moment you create a gap, this empty space will be filled by the nearest electron or the other layer electron. So either this will try to come, or this will try to come, or something from here. So they will try to come. Okay. So now because they can come from anywhere, you tell me which electron will have the highest probability of coming here. Okay. So the electron which will have the highest probability of coming here will be from the nearest element, isn't it? Am I audible to you guys?
Yes, sir.
So tell me which electron will have the highest probability to reach the empty space, the nearest one or the farther one? So if we have the empty space in the, let's say, K shell, if we have the empty space here, then which electron, like electron from which orbit can come here easily? K is the empty, so L, M, or N, which can come here easily? Tell me. No idea. So we have electron. This is the nucleus. This is the empty space. Now, once you create the empty space or the vacuum, the electron from this can come or this can also come. So now the question is which can come easily? Tell me which can come easily. So if there is some emergency in your home, then who will come first? Your neighbors or the your friend or a relative from abroad? So I'm creating the empty space in the K shell. So who can come fastest or easily? The electron from the outermost shell or the nearest shell?
Yes, sir.
So the probability of if this is K shell, so if K shell will have the empty space, then which shell electron can come easily? The L shell. So the probability of L shell coming to the K shell is highest than the probability of coming from M shell to the K shell. So when an electron will jump from the L to K, it will emit the photon, and this photon will have the energy which we write as Sc by lambda K alpha. And if you come from the M shell, it will also release a photon we call K beta. So tell me energy wise, which one is more energy, the K beta or K alpha? Energy wise, which one is having more energy? The M to K transition or L to K transition?
Right.
So if you go back to the diagram, You can look at here. Intensity is high for K alpha, which means this is a highly probable event. But if you look below, which wavelength is lesser, alpha or beta? This is lambda K beta, this is lambda K alpha. Clearly, the lambda K beta is a small wavelength, and for the reason it is having high energy. So it is having the high energy, but the probability is less. So we have the smaller spike. This is having the low energy, but the probability is high, so big spike. And similarly, you can have the other diagram, the L alpha and L beta. Okay. So the whole idea of the spikes are to represent which event is more probable. Understood? So bigger spike means more probable event, and low spike height means less probable event. So basically, this is the intensity here is the number intensity, not the energy intensity. This is the number. What is number intensity? Number of photons leaving the surface per unit time per unit area. So it is not the energy in sense of energy. It's dn upon ad. So that is the meaning of intensity here. Okay. Is this clear? So energy lost by colliding. Okay. So first of all, we need to understand the nomenclature. So if we have, so let's say if we have the empty space in the K shell, then every wavelength, so because the K shell electron is going to be filled, the name will be K. So all wavelengths will be called lambda K, lambda K.
Call from +919893223822.
Now, when the transition will happen from the nearest shell, we call alpha. When it is happening from the next nearest, we call it beta. So going by this convention, we can call this as gamma, delta. So generally, what you will encounter is alpha and beta only. The gamma and deltas are not taken into any question. Now, what happens if we have the empty space created in the L shape? If the empty space is created here, so the electron will come from either M to L or. Now, what you need to also remember that from lower electron will not go to higher shell because energy wise it is not a lower energy configuration. The whole idea of atom is to attain the lowest energy configuration. So only high energy electron will try to come to this level in order to make the low energy configuration. Okay. So in such case, the naming will change. This is called lambda L alpha. This we can call it lambda L beta. So you can also have the M alpha, M beta, M gamma, then N alpha. But those are very, very, very small probable events, and so the first two events are only considered for most of the experimental purpose. So now Mosley only studied the K alpha X-ray, like the innermost transition. Now also the reason of studying K alpha that this is the most probable event. Now what does it mean? So knocking off the innermost electron is the easiest job. Now you may ask why. So if we talk about the Bohr's idea of atom, and if we think of electron in every shell, and if some external electron is coming, then which electron is easiest to knock out? The innermost or the outermost? And if I mean if your answer is whatever, then why is that answer? Tell me. So which event is most probable? Anybody tell me. So which probability is highest to knock out the innermost or to knock out the outermost?
Outermost.
Question is, if the outer electron is coming, then which electron will be knocked out easily, innermost or the outermost? Okay, so again the answer is innermost, and the reason is we have to think of the Heisenberg uncertainty principle. So if you go from the innermost to the outermost orbit, the uncertainty in the position will increase, and because of the uncertainty in the position will increase, you have the big area to cover, big surface to cover in a three-dimensional world. So hitting is very less probable event because we don't know exactly where to hit, and the innermost shell is confined into the small surface, so we can say the chances of hitting is very high. So as a natural event, the emission of innermost electron is most probable event, and that is why the K alpha is the most probable X-ray, characteristic X-ray. So the K alpha is basically your characteristic X-ray, and it is most probable event also. And that is why if you look at the first diagram, the graph is highest, the peak is highest. You can see here, okay, because this is the most probable event, and these two events are happening. The removal of electron from the L cell is not impossible, but the event is less probable. So we have the smaller peak, and other events are even negligible, or very poor in terms of probability, and so they don't have significance on this graph. Although you can draw some of them. Okay. So understanding the graph of X-ray is quite fairly simple. So these are the blue lines are the X-ray due to the loss of kinetic energy, and there is also very nice German name to this, and this is called uh,
Call from India +91 849745849.
so this is called the Bremsstrahlung radiation, and this is the German word which means breaking radiation. So and the name is apt name because it is breaking the motion of electrons. So you break their, it's like a breaker. So the moment they enter the target material, uh, they face many obstacles and their speed is decreased, and so the kinetic energy and the loss of the kinetic energy appears as X-rays. Okay. So now you know the event wise which one is possible and why we have some more bigger spikes and smaller spikes. And now if I draw something like this, in examination we will come across various relationship. So for alpha we can have we'll stop here. For L alpha, L beta, L gamma, L delta, M alpha, M beta, M gamma. Let's go there. So this is called, because this is K. So this is called lambda K alpha because you're coming to K shell. So all these are K. This is K series. This is called L series. It's called M series. So lambda k alpha will be equals to EL minus EK upon HC. You can write like this. And I have it in wrong way. So EL minus EK equals to HC by lambda k alpha, like this. Now tell me EM minus EK will be how much? HC by lambda k beta. So the next we can call it beta. And if you write the En minus Ek and so on, EO minus Ek. So this is for K series. So for L series, what you can write? So for L series, the starting point is L. So the nearest is M minus L, and you can write is L alpha, M N minus L, beta, Mn O minus L, and if you want, you can write M series also. So the N will the first one, En minus Em, M alpha, and so on. Okay. So I hope the nomenclature is clear to all of you. Okay. So these are the nomenclature that we have to use, and there is a very famous question. Let me give you that question. So EKL minus EK SC by K alpha, and M minus K is KLM. Yeah. And N alpha is, so they will ask you what is the relationship between these three, and it's very easy. The 2 minus 1 is equals to 3, right? So if you subtract 2 from 1, you get AC into 1 by lambda k beta, lambda k alpha is lambda L alpha. So 1 by lambda k beta is equals to 1 by lambda k alpha plus 1 by lambda L alpha. This is a very famous relation. They ask the which of the following relation is true. You can derive it writing the formula like this. So So the last concept of this chapter is called the Mossless equation. Obviously, Mosley law. So Mosley law is basically a relationship between the atomic number and square root of frequency of characteristic X-ray K alpha. So to derive the Mosley equation, we have to use the Rydberg formula, which we know that 1 by lambda is Rydberg formula into 1 by like. So from the Bohr's theory, we have this relation 1 by lambda into R into Z square 1 by N square minus 1 by M square. Then this is Bohr's so this is from Bohr's theory for single electron system. So hydrogen, helium plus or lithium plus plus beryllium plus plus plus. So as long as we have the single electron system, this formula is true. So what happens if we have the multiple electron system? So for multi electron system, so for multi electron system, the first thing we need to do is modify. We have to consider the shielding or screening effect. So the Z must be modified to a new value called Z effective, and Z effective is defined as the Z minus screening constant. So B we can call as, so this is the first step that we need to be careful. So we cannot write the Z just like that. We have to write Z as Z minus B, because if we have multiple electrons, then the nucleus cannot apply the same force on the electron effectively as in the case when there is no electron. Rather, some of the electron will try to shield the nuclear effect. So I hope you have heard about the nuclear shielding in chemistry. And so the modified formula will be of the modified Rydberg formula that we can use roughly. So modified Rydberg formula for X-ray will be and what it will be 1 by lambda equals to r z minus b whole square. So if you multiply with hc, this becomes the energy relation, not at hc. If you multiply with c only, and c by lambda is called frequency. So frequency will have the formula. So if you plot the graph between frequency and the atomic number, you will get a quadratic equation. So to make a linear relation, we can make it a square root. Taking square root both sides, the frequency will be under root of and this will become a linear function z minus b. This entire term has nothing to do with the metal, rather it is called transition constant. That is, it only depends on which two orbit the electron is transferring, and no matter these two orbit belongs to which element. So if the n and m are fixed, this will have the fixed answer, and n and m belongs to any element. So this is not depending on the element, rather on the transition value. Therefore, this notation we write as A into Z minus B. And so you can say this is AZ minus AB. So if I call this as y-axis, this becomes mx plus C graph. And if you compare, so y is root of frequency, and the slope is the transition constant, and the intercept is minus A. So if you try to plot this graph, so if you try to plot the graph between the square root of frequency and the atomic number z, so you will get roughly this picture. So as I said, X-ray cannot be emptied by all atomic number. So graph will be only valid beyond certain number, and the rest we can extrapolate the graph. This is minus AB, and if I call this as theta, then tan theta is the A, and the A is under root of RC is 1 upon. And when he actually plotted the graph of every Z and every square root of frequency, he got a scattered plot. And this is the, you can say, best fit line, which means it is somewhere passing through the center of all the elements. And because of this proportional behavior, Mosley proposed the uh, the concept of modern periodic table, and he said that the chemical and the physical and the chemical properties of an element is directly or is actually not directly is a periodic function of atomic number, what Mendeleev said as atomic mass. So that change from the atomic mass to atomic number was the biggest change in the world of science. And because he was in the World War II, so he died in the World War II fighting. Maybe because he was genius, so many scientists got scared of him and might have killed also. No one knows. Sorry. So this transition constant is independent of the element, but it depends on the transition. But the B is something called, so B depends on the basically electronic configuration. So B depends on the electronic configuration. So G at, because every atom will have its own configuration. So B depends on uh, element. It's good to say. So among A and B, B depends on element and A depends on the uh, transition that we talk about. Like for example, for K alpha, now you can choose any element. I mean zinc, cobalt, copper, whatever. The K alpha will have fixed A value, but B will depend on element to element. So let's say if you have the copper and K alpha, then B will have one value. Chromium and K alpha, different value. Cobalt and K alpha, different value, but A will remain same in all the elements. So for K alpha, the value of A is under root of RC, and because it's a K means N is 1 and M is 2. So this becomes under root of, this is the value of K alpha. Okay. For K beta, the A will be, this is 1, this is 9. It becomes 8.9. Now there is one value of B which we know, rest we they will give in the examination. So for K alpha, the B we take as 1 by default. For other transition, so K alpha means transition is like this. So the equation becomes so you can solve any question of X-ray using the formula. So let's solve some question. Do you have S Verma? Anyone? Am I audible, guys?
Yes, sir.
Hello, hello, 1, 2, 3.
Yes, sir. Yes, sir.
So this is the Davison-Germer experiment, and the last concept from the this part will be. But I hope this is done in chemistry mostly. Have you done the Bragg's law? So Bragg's law of X-ray diffraction. So this method is basically employed to understand the structure of metal. So metal having the lattice behavior or lattice shape or structure. Lattice means they have the fixed geometrical arrangement, and because of this fixed geometrical arrangement, they can create the interference pattern. So if I draw some, okay, so every intersection is like a atom, think like this, and you can see there is a spacing between the atom, and this we call the lattice spacing. So lattice spacing is measured between the layer, not along the layer. So the beauty of metal is that they have the lattice structure. So atoms are quite arranged in a geometrical fashion, and these atoms are having some separation, which is very small, and they are so small that normal wavelength cannot enter the metal. But X-rays are very small in size, so they have quite a good penetrative power. They can go up to few layers below, and gamma can go even further. And cosmic rays can actually go even millimeters within the metal, that is millions of layers they can go inside cosmic rays, and the neutrinos can go to any depth which you cannot imagine, which means they can go through anything. I mean, neutrinos cannot be stopped. That's good. So now how we can understand the lattice spacing in using the experiment of Bragg's law diffraction method. So this is the incident X-ray, let's say at the first layer, and it gets reflected and goes this way. The next will come. Sorry. So you can see that the two X-rays are coming, and the first one is hitting the first layer, and second is hitting the second layer. If I say this angle is theta, if theta is the angle of the incidence, but we take from the horizontal instead of vertical. Then if I draw a perpendicular from here to here, so these two rays will eventually meet. Let's say we have something like this. Generally we obtain on a screen, and we see the diffraction pattern actually. So from the concept of interference, if they interfere constructively, then we get the maximum. So if the lattice spacing is like this, then the path difference will be this length, the extra length from here to here. So from beyond this point, they have traveled same distance, and beyond also same. And D is the lattice spacing. So this is equals to the path difference. If you try to calculate, will be 2D sine theta, and the difference nothing but the from A to B basically. So A to O to B. This is A O. So the delta x is 2D sine theta. If you do the geometry, you can get the answer. And for maxima, the path difference should be integral number of wavelength of the X-ray. So if you put n equals to 1, you will get the smallest spacing. So the D minimum we can get is lambda upon 2 sin theta. So that is how we keep on changing, we keep on varying the theta, and at one particular theta we get the maximum intensity. So we know that if the theta is known to us and lambda is anyway known to us, we can understand the structure of a metal. So what is their nearest spacing? That also gives the separation between the two nearest atoms in most of the cases. So this is the X-ray diffraction, and the next topic that we are left with is nuclear physics and the radioactivity. So that we consider cover in the next lecture. Okay, bye.
Bye, sir. Thank you.